Okay.
Hello.
ഇത് ഓണാണോ? സൈഡില്ല ഒരു പ്ലസ്.
അതിന്റെ മൈക്കിൽ കൂടെ
അത്രയും സമയം മതി. ഇവിടെ നിന്ന് പറയുന്നത് കേട്ടോളൂ.
ഇത് ഓണാ?
ഹെഡ്സെറ്റ് ഉണ്ട്, അത് വെച്ച് അദ്ദേഹം സംസാരിച്ചാട്ട്. അതില്ല ഫോണായോ ഒരു സൗണ്ട് കേൾക്കുന്നുണ്ടോ?
ഹലോ കാരണം ഇത് ക്ലോസ് പറയുന്നെല്ലാം കേൾക്കുന്നുണ്ട്. ഹലോ
പുറത്ത് പോകാം.
ആ സാറ് പറഞ്ഞു. ഹലോ ടെസ്റ്റിംഗ്. ഹലോ ഓക്കെ. ഹലോ
മറ്റേ വീഡിയോ ഡൗൺലോഡ് ആവുന്നില്ല. അത്
ഡൗൺലോഡ് ആണ്. ഓപ്പൺ കൊടുക്കുമ്പോ അതിങ്ങനെ
ഡൗൺലോഡ് ആയോ? ഡൗൺലോഡ് ആയില്ല. ഡൗൺലോഡ് ആവട്ടെ.
ഇതുണ്ട് ഒരു എക്സ്ക്ലമേഷൻ മാർക്ക്.
സാർ അത് ക്ലോസ് ചെയ്തു.
ഓക്കെ. Mike. Stop sharing.
Good morning, everybody from New York. I hope that you can see, you can hear me well.
Sir, hello.
Yeah, can you hear me?
Yeah.
Okay, perfect. So just a second, I'm going to share my screen. Can you please tell me whether you can see my slide? Okay, I hope that you can hear me well, you can see my slide. Good morning, everybody from New York. Thank you very much for inviting me to this very important event. I'm going to make a presentation related to the experience of the United Nations Joint Staff Pension Fund with digital identity. You cannot hear me. Range. Can you hear me now?
Sir, hello.
Yes, can you hear me now?
Yeah. Sound. Can you increase the speed? Sound, sir.
Yes. Can you hear me now? I can hear you very well.
But your volume is less.
It's not coming through. Strange. I can hear you very well. Can you hear me? Can you hear me? Can you hear me? Can you hear me now? Low level volume. Huh, strange. Let me see if I can. Let me check. Is it better now? Can you hear me now better? Can you hear me better? Okay, perfect. So thank you very much. I trust that you can hear me, you can see my screen and my slide. So I'm going to make a presentation about the experience of the United Nations Joint Staff Pension Fund with digital identity. And I have here with me today few slides. So first and foremost, few details about myself. I'm currently the Deputy Chief Executive Officer of the United Nations Joint Staff Pension Fund. I was previously the Chief Information Officer of the organization. And before, I was the Chief ICT Auditor of the United Nations. I've been with the United Nations for 25 years here in New York at the headquarters. Few details about the UN Pension Fund. The UN Pension Fund is the pension fund of the entire United Nations system. We serve 25 member organizations and international organizations. Here on this slide, you have some details about the volume of transaction as well as the number of clients that we are serving. In total, approximately 250,000 individuals between 150,000 active participants, basically staff member actively working, and approximately 84,000 retirees and beneficiaries that live across the globe in more than 192 countries. As of today, the current market valuation of the pension fund is approximately over $100 billion, approximately $108 billion. These are some of the emblems and logos of the various United Nations entities that are part of the UN Pension Fund. You will probably recognize some of them. They are very well known. In addition to my role and function at the United Nations Pension Fund, I also have different assignments across the UN system, and in particular, in the Internet Governance Forum. I am the representative of the Intergovernmental Organization to the Multi-Stakeholder Advisory Group of the UN IGF, or the UN Internet Governance Forum. I also co-lead with May Siksik, who you just heard her presentation, a specific working group that technically is referred to as a dynamic coalition on emerging technologies. And I also co-lead another similar working group on blockchain assurance. So very briefly, what is the Internet Governance Forum? Is an initiative created by the United Nations 20 years ago that is intended to be multi-stakeholder, meaning bring together not only UN entities and official representative of member states, but is also intended to bring together representative of the private sector, of academia, non-government organization, civil society, as well as technical community. So just for example, Microsoft, Meta, Google is represented in this initiative, ICANN is represented in this initiative. So it's a global initiative that it's based on a year-round process, that is intended to address issues, topics, challenges, proposal opportunities to maximize the digital technology. And it has an annual meeting that takes place usually during the last quarter of each year and lasts for 1 week, where different workshops, presentation, and discussion are taking place. And then it's all documented in a report that goes to the General Assembly of the United Nations and its various committees. So specifically, speaking about this dynamic coalition or a working group that is co-led by myself and by May, we have created a very focused and dedicated group on emerging technologies. And we have basically defined the mandate, the intent, the goal of this working group in shaping the future of innovation through responsible, ethical, effective, and globally aligned principles that are also, of course, aligned with the Sustainable Development Goals of the United Nations, as well as the most recent Global Digital Compact. And what we are aiming at is to develop terms of reference, to develop modalities, frameworks, processes to identify risk in using emerging technologies, in developing mitigating controls, and in helping organizations either to self-assess or be assessed for the effectiveness. So ultimately about ensuring compliance with this high-level principle in the use of emerging technologies. So what I'm going to share with you today is a specific initiative that I had the privilege to lead since 2017 when I became Chief Information Officer of the United Nations Pension Fund. And the whole started with the 70-year challenge that the UN Pension Fund had in determining that its 84,000 retirees and beneficiaries that receive payments every month and that live across the world in more than 190 countries are indeed still alive. So the way that for 70 years, the UN Pension Fund determined that these individuals were still alive was through this form that you see on the screen that was mailed every year through 190 postal services by sending them this form, asking them to sign this form and return it as a proof of their existence. Now, as you can imagine and appreciate, this process was often subject to delays, to lost form, to problem vis-a-vis the receipt and the sending of this document back and forth between the pension fund and the retirees and beneficiary. And unfortunately, sometimes led to very negative consequences because if by the end of the fiscal year the UN Pension Fund did not receive this signed form, had to stop by rules or regulation the payment, with of course very negative impact on the sustainability of the family, of the household, of the intended recipient. So the way that this problem is being resolved was by creating a digital version of this process, by creating an application that uses a biometrics, that uses facial recognition, that uses blockchain, and that uses also artificial intelligence. And I will speak to this use of emerging technology and to aspects associated to the assurance and auditing, given my background in this discipline, in order to make sure that the governing body, the stakeholders, can rely on the trustworthiness, on the security, and on the sustainability of this application. And indeed, in order to achieve this goal of providing assurance, I certified this application in accordance with several ISO certifications by always maintaining a compliance and alignment with the Sustainable Development Goal, and also by receiving some important recognition and awards, such as the UN Secretary General Award on Sustainability and Innovation, and such as also being a case study of Gartner that published a study exactly on our experience and our use case. So this is in detail the problem. Was about transforming a 70-year-old manual process based on the form, again, that you see depicted on the slide, that involved more at that time in 2017, 70,000 retirees and beneficiaries residing in more than 190 countries using paper-based form, transmitted through 190 postal services, prone to delays, lost form errors, and causing, as I indicated before, suspension of payment when that form was not received. But overall, one of the biggest challenge that the pension fund of the United Nations always had was that our board, the General Assembly, which is composed of representatives of 193 different countries, always questioned the fund. How can you prove that there is no fraud? Now, this is a negative proof, and as you can appreciate, it's impossible to provide a negative proof. So the solution that we designed to respond, to address this question, was through a positive proof, through the use of the technology that I mentioned before. And this, excuse me, and this is in the screen, the exact screenshot of the announcement that in 2021, we published on our internet website announcing the deployment of this application, of this solution. So this solution is being into production since 2021, and today we have 60% of our retirees and beneficiaries around the world using this application to confirm every year that they are still alive. This is an infographic that the British Blockchain Association created for us, trying to represent in one slide all the key components of the solution, from the challenge to the key technology to the security compliance, the impact and benefit, the core feature, and the deployment adoption. I'm not going into details, so you will receive a copy of this presentation, and if you have any question, you can always contact me offline. So we moved from a process that was highly centralized, where we from New York, as I alluded to before, mailed this form to each of those 84,000 retirees across the globe, through a process where we reverted the direction by enabling, by supporting our retiree in downloading this application and being enrolled into this application. We allow them to confirm and to take the input and the initiative of confirming every year that indeed they are still alive without us triggering the process. So how did we break down the problem? The problem was broken down in the need to provide 4 proofs: proof of identity authentication, proof of existence, proof of transaction, and proof of location. So how did we do that? By using a blockchain to create an immutable, independently auditable and traceable triple entry distributed ledger, where we have a sender, the retiree, we have a receiver, the UN pension fund, and then an hashing of each event associated with this transaction. We use biometrics, specifically facial recognition, that is stored only and exclusively on the user device to authenticate the user, but we event recorded on blockchain. And we do not store and we do not transmit biometric information at any time. Once each one of our users goes through the process of being enrolled, they are guided in capturing their biometric profile on their own device, and then remaining on that device, they conduct the proof of life every year. We also adopt artificial intelligence in order to fight AI with AI, because by using biometric facial recognition, we became very concerned about the potential use of deepfakes. And therefore, we have embedded in our biometric algorithm a module that detects not only whether there is a picture on the other side of the phone, but also whether that picture is indeed a real picture of a human being and not synthetically generated images. And now we have submitted this biometric algorithm to a specific test conducted by an independent entity in accordance with this ISO standard that basically describe and provide all the different tests that can and should be conducted to confirm whether a biometric algorithm can withstand presentation attack or deepfakes. And we also use the GPS, the Global Positioning System, because in certain cases, we also need to collect information related to the location of the user when they confirm to be still alive. So the application, it's an open source application from the Linux Foundation that is part of the Hyperledger framework. And in particular, in this ecosystem, we selected the Hyperledger Indy, which is a blockchain dedicated to support decentralized identity, and Hyperledger Areas that provide the associated libraries. This is a screenshot of the application itself, that it's available both on the Apple Store as well as the Android Store, where any one of our client, our retirees and beneficiary, can download on their smartphone device. These are other images and screenshot of the application, and these are the ratings and the review that after 4 years we have been able to obtain. Now, in 2024, the General Assembly of the United Nations declared 2025 the year of quantum. And of course, again, as a former auditor, I started to be always concerned about how I can provide assurance about the security, about the trustworthiness of the application itself. And in so doing, the quantum threat became one of my concerns. And I started to take action on how to make sure that the cryptographic primitives that are used in the blockchain that support the application can be migrated to post-quantum resistant cryptography. And in so doing, I started to define the problem, and specifically focusing on the issue of harvest now, decrypt later, because I wanted to make sure that the transaction, the data recorded on blockchain as an attestation, as a proof of the reliability of our process, will always remain integral. So this is another way that I started to communicate to the various stakeholders the concern associated with the harvest now, decrypt later, that today ill-intended individual may store offline our transaction and then wait for the future when post-quantum computing will become a reality, capable of decrypting our data and access not just potential sensitive information, but also potentially altering the integrity of the blockchain and the transaction recorded. So I started to go further, and from the overall and high-level concern associated with the harvest now, decrypt later, I started to identify what in my specific solution will be the element vulnerable to this threat. And here you see the list of the key element: the digital signature compromise, the risk to the security of decentralized identifiers, the zero knowledge proof vulnerabilities, the long-term credential validity, and the integrity, as I just alluded to, of the distributed ledger itself, that for us represent the evidence of the reliability for any potential audits and verification. So go even further and going even at a more granular level in the specific platform, the Hyperledger that I presented before, I started to identify the potential element that could be vulnerable to this threat, such as the need to update the method of our decentralized identifier, the dates, the need to identify appropriate signature scheme for the credential, the need to secure the messaging component, the consensus of the ledger, the blockchain itself, and the connection between agents. In so doing, I started to reference the ISO standard, specifically the 15408. I started to consult with my team NIST publication, technical white papers and literature, and also, of course, started to work in collaboration with the provider, the Linux Foundation, that supports the ecosystem and the platform itself. And here, ultimately, are the data that in my specific and our specific blockchain are most vulnerable to the quantum threat. The transaction validation data, the root hash, the transaction type, transaction timestamp, and the sender public signature. So I narrow down and focus on the specific element potentially at risk. Identify the potential solution, such as migrating, upgrading the cryptographic primitive to lattice-based cryptography, to hash-based signature using scheme that have been tested and approved, such as Sphinx Plus, upgrading hash function, and where possible, adopt a hybrid approach. And so this is the path to upgrade that we have identified with the vendor: the dual signature support, the quantum safe DID method, the zero knowledge proof upgrades, and the enhanced quantum key distribution. And so ultimately, some lesson learned. What did we learn? We learned that it's important not just to look at the technical solution to upgrade the cryptographic primitive, but also look at the data retention, what type of data is stored on the blockchain, what is the cryptographic inventory in the entire ecosystem of each organization within the blockchain is used, look at the critical system identification, look at the technical debt analysis, and of course, at the third party that work with us in providing their software application. And of course, we also identified some best practices such crypto agility, adoption of a hybrid approach, adopting the defense in depth layer approach, and trying to adopt also a philosophy of future-proofing the solution. And these are ultimately the conclusion that we reach vis-a-vis how to pursue and how to ultimately implement our approach to enhance security of digital identity. So I'm going now to conclude by sharing with you the assurance aspect to the application. As I alluded to, being a former auditor, this was in parallel to the design and implementation of the solution, always a constant concern. So we certified the application with ISO 27001 standard for information security, with the ISO 27701 for the protection of privacy data. We are the first and for now the only UN entities that achieve the certification on ISO 42001 on the responsible use of artificial intelligence, as I alluded to before, as embedded in our biometric algorithm to prevent and detect potential deepfakes. And we are currently submitting the application to this other ISO standard to confirm that indeed the biometric algorithm works as expected. We also conducted an algorithmic assessment. We submitted the biometric algorithm to this free available survey that the NIST provide in testing on a periodically basis the algorithm for face recognition evaluation of the technology. We also conduct a cybersecurity assessment in order to obtain the ISO certification and also a privacy data assessment. So in benefit, we eliminate the paper, we eliminate the printing, mailing, archiving, both logical as well as physical. We enhance the signature verification. We optimize the blockchain by creating redundancy between two platforms. And we also evolve the solution. After 2-3 years of implementation, we realized, for example, that in certain parts of the world, some of our retirees and beneficiaries did not have an adequate smartphone that could have been used for the application. Therefore, we created a kiosk mode, which is a replica of the application that runs on iPad, that we installed in specific local offices of the United Nations, where our local retiree can visit and perform the process of confirming they're still alive. And also another initiative that derived from our implementation was that the UN, and in particular the highest coordination body, the Chief Executive Board, realized that when we went live with our application, we had created a digital identity solution for when staff members leave the organization and retire. And so they decided to use the same technology to actually create a UN digital ID for all staff members since the moment they are hired throughout their careers. And that it's a project that now it's ongoing and already brought together 6 UN entities. So, as I alluded to at the beginning, we received some important acknowledgement, the award of the Secretary General of the United Nations Innovation Sustainability, the award of the Government Blockchain Association of Social Impact, and also being recognized as a case study by Gartner with a published document on their repository of documents. And also the British Blockchain Association last year invited us at their 7th Blockchain International Scientific Conference, and we received an award as a second project that was examined, a peer review by the subject matter expert of the British Blockchain Association. Indeed, the British Blockchain Association was so impressed that in writing to the Prime Minister of United Kingdom, they mentioned us, the text that I highlighted in yellow, I don't know whether you can see on the slide, as one of the meaningful example of adoption of the blockchain technology for a digital identity. And there was also an article from Pension Tank, an industry document that they wrote about our experience. Here in this slide, I just share it for the fact that in 2024, when I made this presentation, the World Summit of Information Society, an event coordinated by ITU, the International Telecommunication Union Geneva, I had the honor to share the stage with Scott Stornada, that is one of the images, a picture you see here, who, for those who know a little bit about the history of blockchain, is indeed the co-inventor of the blockchain technology together with Stuart Haber. Other collaboration, we, as I alluded to at the beginning, we are very active in the Internet Governance Forum with May. We're sharing examples such as the one of the UN Pension Fund. We also working with the ITU in the Metaverse initiative, specifically the one on Cityverse, along with many other organizations, and specifically in Track 5 for the evaluation assessment of the use of emerging technology in the metaverse. These are some of the emblem and logos of the organization that participate in this initiative. And indeed, one other collaboration that is very important was the one with Interpol, where last year invited me to present their conference on artificial intelligence and digital forensic. So thank you very much for your attention. Please let me know if you have any question now, or if you want to contact me offline, I would be more than happy to reply and respond. Thank you.
Thank you for your such a good speech and information. We are really inspired by your words. Thank you, sir.
Thank you very much. Thank you. Thank you for your time.
Our videos.
Did you say?
Yeah, so he wasn't
Is it?
seeing anything.
What's that?
Yeah, actually, video was off.
Yeah.
It's not on the camera. It's on the Very nice standard.
നമ്മുടെ
Researcher in the field of quantum biology to deliver the keynote address titled Quantum Biology When Physics Meets Life, a New Frontier for India.
Oops. Hello, everyone. I'm trying to open my slides. Just a second. Here it is. Thank you. Oops. Can you hear me?
Yes.
You can, right? Can you see my slides?
Yeah.
Can you see the slides change?
Yes.
Awesome. Hello, everyone, and good evening from sunny California. It's a pleasure to be talking to all of you. And today I am going to talk about something that is not
Ma'am, hello.
enough talked about. Yes.
Ma'am, actually, your slides are not changing.
Does it change right now? Does it
Yeah,
go to a blank page?
Yeah.
Okay, so it's because I didn't change them yet. So if they still don't change in a second, you let me know.
Actually.
I want to start by telling you a little bit about quantum biology and the flavor of quantum biology that I study that has to do with the action of tiny magnetic fields on the order of those produced by your cell phone on biology. And the cool thing is that tiny magnetic fields throughout many, many decades have been shown to alter all those processes that you see on my slide, from how much respiration cells make, to how much cells proliferate, to how much oxidative stress is made, to how much DNA gets repaired, to ion channel functioning. And this has been seen throughout the tree of life and for many different types of cells. And this is consistent with being driven by a quantum phenomenon. Okay, so that's the take-home message. And I think that there are ways of us harnessing those endogenous quantum knobs in biology for things, for example, for therapeutics, for other things, for biomanufacturing. So let me start with my story. I am a quantum engineer. This means that I build instruments to study and control things that are so small and so well protected from their environment that they're better described by the laws of quantum physics, as opposed to the laws of classical physics that rule everything big around us. So people get a little bit surprised when I say that I study things that might be going on inside birds and in fact inside all cells. And that's because I'm a quantum engineer interested in how quantum physics informs biology at the nanoscale. So before I explain where I'm going, I really need to tell you where I come from. I am trained in a field known as technological quantum sensing. The idea is that you can unambiguously mathematically prove that if you use a quantum object, like an electron, as a sensor, your measurement is improved. In other words, the sensor quantumness enhances the measurement. In my past, I worked with a quantum sensor that works at room temperature and in noisy environments. It was a technological quantum sensor, in fact, an electron diamond, the material diamond. But the talk today starts with proteins, because chemists have known for many, many decades that particular electrons inside a particular class of proteins are quantum sensors, for example, of magnetic fields. And I'm going to tell you exactly how this works, okay? And the talk is going to end a little bit further in the biology, because those things might be happening inside cells and not only inside test tubes. Okay, so just to put all of us in the same page, the quantum object that I'm going to tell you that is a quantum sensor is an electron spin. So spin is a fundamental property of matter, and it's as fundamental as charge and mass. In the same way that mass measures how an object interacts with a gravitational field, charge measures how an object interacts with an electric field, spin measures how an object interacts with a magnetic field. In the same way that charges can be positive or negative, meaning a different interaction with an electric field, spins, that's just a convention, are said to be up or down. They're represented by an arrow. And spin up or spin down gives rise to different interactions with the magnetic field. Everything has a spin, even if the spin is zero. For example, electrons and atomic nuclei, and spin is really the star of what I'm going to tell you, because it's been known in chemistry for decades that there's a broad class of spin-dependent chemical reactions whose microscopic final products can be tweaked, macroscopically changed via the application of tiny magnetic fields. In chemistry, here's how this works. There's a chemical reaction happening, doing its thing in the test tube. At some point, the chemical reaction comes to a crossroads. At that point, the chemical reaction is going to actually look for the spin state of one particular electron. If the spin is down, the chemical reaction is going to continue through a branch, giving rise to, say, the yellow products that you see there. If the spin is observed to be up by the chemical reaction, the chemical reaction continues through a completely different branch, giving rise to, say, the red products that you see there. However, electrons are quantum objects. This means that in the presence of a tiny magnetic field, an electron that is spin down can be put into a superposition of spin down and spin up. If you have never heard of superposition, here's what it is. A superposition is a funky quantum property of quantum objects, and it's akin to an object having two properties at the same time. If a ball were quantum, it could be said that maybe it could be in a superposition of being red and green. In our macroscopic world, it doesn't exist, but in the quantum world, it does. And I like to think about superposition as a dimmer switch. That is, it's a bit spin down and a bit spin up, and like in a dimmer switch that can leave a room entirely dark or entirely lit, the position of the dimmer switch tells us if it's darker or as if it's brighter. So I like to think of the superposition as a dimmer switch. Now, everything that starts classical quantum dies classical. This means that after a short time, the superposition goes away, the quantumness is extinguished, and basically the electron spin becomes more of a flip switch. It can be either up or down, but for a short amount of time, magnetic fields are going to be able to put the electron spin into this dimmer switch superposition state. So, for example, this blue magnetic field puts the electron into a particular superposition, and the experimental consequence of that is that if you have many molecules undergoing this chemical reaction once, or one molecule undergoing this chemical reaction many, many times, on average, the experimental result of the superposition is that you're going to produce a mixture of macroscopic final products of only spin up and only spin down by a proportion that depends on the position of the superposition, of the dimmer switch, which itself is a function of the external magnetic field. In turn, for example, if you put a slightly different magnetic field, a green magnetic field, experimentally, the final products are going to be another mixture of products only spin up and products of only spin down by another proportion. Now, some consequence of that. This is absolutely known in chemistry. So this only works while and because and while the superposition lasts. I'm going to argue soon that the superposition is actually being used as a resource to do the sensing. Even though the superposition is very short-lived, because the superposition makes the decision of which branch the chemical reaction is going to take, the consequences of the superposition are felt macroscopically because it changes the products and at much longer time scales. Okay, when the products are formed, the quantumness has been gone for a long while. Okay, so this is an effect that is, if you will, scale shifting. Fast things at the very tiny scales end up having a macroscopic consequence at much longer time scales. Okay. Second point that I won't have time to explain why, but it's 100% understood in chemistry. The magnetic fields that can actually alter the equilibrium of this chemical reaction are relatively small, on the order of your cell phone. And this is really funky because this means that if you have two very large enough magnetic fields that are different, the final products are going to be similar. Two different magnetic fields are not going to be able to alter the final equilibrium of the products of this chemical reaction. This is absolutely understood why. Okay, so, and it's very interesting because if you plot the magnitude of this so-called magnetic field effect as a function of field strength, it does not only go up, it does not only go down, it goes up and down. So here, more is not necessarily better. And third, I'm going to point out that this type of sensing the magnetic field is exactly what a card-carrying physicist would call quantum sensing. Like in the simplest modality of quantum sensing, here it's the superposition being used as a resource. It's the superposition actually that is reacting to the field. So this is bona fide quantum sensing happening inside proteins, and this has been known for a long time, unambiguously demonstrated at room temperature in liquids, solids, and gases for magnetic fields as tiny as the Earth's, which in turn is way orders of magnitude smaller than the magnetic field of your cell phone. Okay, this whole shebang goes from chemistry to biology because of birds. People had been trying to explain how birds migrate because they do so using at least as a partial cue the magnetic field of the Earth. They have a little compass, and people were trying to understand how they do so. In 1978, a brave theoretical physicist made a bold hypothesis. He hypothesized the following. Well, were the same type of electron spin-dependent chemical reaction be happening inside cells, inside birds and other organisms, birds and other organisms might react to magnetic fields to the extent that they would react to the different final products of the chemical reaction. Okay, so the bird is not doing quantum sensing, the bird is only reacting to the final products that are modulated by the magnetic fields. All is well, except that there are physicists in the room. There's certainly someone who's anxious because this hypothesis is in principle outrageous, because the profound implication of that is that if birds are using this mechanism to migrate, the profound implication is that electron spin superpositions are maintained inside the cells of the birds for long enough, and we can quantify long enough, it's not super long, for long enough to work as a resource. Everything that starts quantum dies classical. There's a reason why quantum computers, they are built, for example, at low temperatures in a vacuum. Quantumness does not like things that are hot, warm, hot and messy. Okay, so it's it might come as a surprise, the possibility even that superpositions might live inside cells for long enough. And I'm not going to explain, but for example, long enough, if birds are sensing the magnetic field of the Earth to navigate, this implies that electron spin superpositions are maintained inside cells for about 700 nanoseconds. This is not super long, but this has not been unambiguously demonstrated in any experiment on Earth right now. Okay, and this is what my group is after. We need to think about the timescales. Well, but this was a nice theory in any case, and it sort of was consistent with the ways that birds behaved with experiments done with birds. And birds fly in a way that is consistent with what this theory predicts. So biophysicists started looking for because birds, animal proteins that were able to sustain electron spin dependent chemical reactions. And the first animal, because birds, the first animal protein that was shown to be able to sustain electron spin dependent chemical reactions was this molecule that you see there, which is called a cryptochrome. Now, cryptochrome is a flavoprotein that has a chromophore called a flavin. And cryptochrome is present in the eyes of birds, in the antennas of migrating butterflies. And surprise, surprise, cryptochrome is also present in all your human cells, except in your germ cells, because it also has circadian rhythm regulation functions. Okay, so yes, we in principle have the hardware to sense magnetic fields. If the hardware is connected to some software downstream, we do not know, but I assure you, probably in all your cells, there is hardware to sense magnetic fields. Okay, but again, my point here is that this is not a talk about birds, and it's not a talk about cryptochromes either only. Okay, cryptochrome was the first molecule described in the context of birds. But again, all of those processes that you see there have been shown to be tweakable by magnetic fields in a way that is consistent with this quantum theory. Okay, again, it's a lot of stuff, from how fast cells divide to how much energy is produced. So, and in fact, people find heuristically magnetic fields that do stuff, and then they roll with it. There are many companies that are actually, I trust what they do. They found magnetic fields to reduce brain cancer, to reduce the size of breast cancer, to do, to the right here, muscle regeneration in athletes and the elderly, and even increase the yield of lab-grown meat, all with the help of tiny magnetic fields. Again, they do not know the mechanism, okay, but they find those magnetic fields and they roll with it. It works, but we never know where we are in the space. If you are in a local minimum, local maximum, we don't know. Like, you can never predict yet which magnetic fields do what. So the phase space is huge. There's like magnetic field frequency, strength, direction, duration of exposure. And I liken it to being in a haystack, grabbing a little bit of hay and finding a needle. This works, but it doesn't make sense, because you're out of luck if you need to start predicting without just blindly searching the phase space. So is there a better way to break clean with this old paradigm? And we think there is. There might be a way to get causal data with predictive power. So I won't have time to explain, but you can build a glorified microscope composed of 4 ingredients that is basically a quantum instrument that, coupled to quantum simulations, can give what we're hoping is going to be a code book with predictive power on how to deterministically control spins in biology for function, to actuate in biology for function. Okay? Imagine if we could deterministically control all of this. This is what we could do. We could have this sort of electromagnetic interventions that do not require genetic engineering. It can be genetically engineered to exacerbate the effect, but the knobs, the quantum knobs, are there. It's not chemical. It doesn't require surgery because everything is electromagnetic, and it penetrates tissue very, very deeply. It's cheap, it's remotely actuated, and in principle, at the hand of anyone with a cell phone. Imagine if you could go to an app in your cell phone and you go there and say, well, today I need help with wound healing. And you click a button and your cell phone produces the magnetic field frequency and intensity that you need to do wound healing. And then you do like this with your cell phone, or you wear a wearable with a certain magnetic field. This could have implications, again, for therapeutics, theranostics, for biomanufacturing. Imagine if you can make insulin-producing bacteria grow faster. That helps. You can increase maybe food security by making food grow faster. And it can also help us with crazy things. For example, space colonization. If you think about this, the places that people want to colonize, Mars, the moon, asteroids, they have a magnetic field that is either zero or very different from the magnetic field of the Earth. And weird things happen when you take away the magnetic field of the Earth. in biology. So if you want to colonize Mars, you do need to understand the effect of tiny magnetic fields on how organisms develop. And finally, I think we can definitely learn with biology on how to build better quantum technologies. I remain convinced that nature is the better quantum engineer that exists. Again, nature has had gazillions of years to try things, but I am convinced it is using quantum effects in biology to function. In fact, we believe there's a basal layer of quantumness in all cells that's our bet, that's our hypothesis, is probably essential for the functioning of the cell. So this is what I wanted to talk to you today. I'm from the Quantum Biology Institute, headquartered here in LA. Don't hesitate to contact me. It's been a pleasure talking to you, and may the quantum be with you. Is there time for questions?
Hello. Thank you, ma'am, for your insights and your valuable time. Hello.
Is there time for questions? Are there going to be questions? No. No questions?
No questions, I guess.
Okay.
Thank you, ma'am. Thank you.
Bye-bye. Thank you. Thanks for having me. It's been a pleasure. Bye.
Bye. Thank you.
യൂട്യൂബ് അല്ല പ്രശ്നം, അതായത് സൂം വഴി വരുമ്പോഴുള്ള പ്രശ്നമല്ലേ.
സൂം എടുത്ത്
ഓണേ
അല്ലല്ല ഇത് ഓൺ ചെയ്തില്ല സർ.
വെളിയിൽ
ഹലോ
ഇത് ഇനിയിപ്പോ ഇതിന്റെ സെഷൻ അല്ലേ?
ഹലോ ഹലോ
അല്ല ഇപ്പൊ വരും, ഇത് നോക്ക്.
ഹലോ
അല്ലേ
ഹലോ
ഇവിടെ ചേഞ്ച് ചെയ്യാണോ?
സ്പീക്കർ മാറ്റണ്ട.
സ്പീക്കർ
മറ്റേതില്ലേ
ഏത്?
6 ഇട്ടാ മതി.
ആ
അത് കഴിഞ്ഞു.
അതിന് നമ്മൾ എവിടെ കേൾക്കുന്നു? അത് ഇതും കേൾക്കുന്നില്ല. അത് ഞാൻ ഇവിടെ കേൾക്കാം.
ഇത് കേട്ട് നോക്കി.
നമ്മളെ യൂട്യൂബിൽ അതിവിടെ അല്ലേ കേൾക്കുന്നുള്ളൂ. നമുക്ക്
അല്ല മിസ്സേ,
ആരുമോ
യൂട്യൂബിൽ കേൾക്കുന്നുണ്ടോ? ആക്ച്വലി യൂട്യൂബിൽ പ്രശ്നം ഉണ്ടായിരുന്നാണ്, അവര് പറയുന്നത് അയാൾ തന്നെ കേൾക്കുന്നുണ്ട്.
ഹലോ ഹലോ ഹലോ
ഇപ്പൊ കേൾക്കുന്നില്ലേ? ഉണ്ടാ
ഹലോ
ഇത് വേറെ എന്തെങ്കിലും ഉണ്ടോ? ഹലോ ഒന്നുമില്ല.
മറ്റൊന്നും സൂമിലാണല്ലോ.
സൂം ലൈവ് ഉണ്ടാവുമല്ലോ. സൂമിന്റെ ആണെന്നുള്ള പ്രശ്നമാണ്, നമ്മൾ സെക്കായ അവിടെയാണ്.
ഹലോ
ഞാൻ തിരിച്ചു കൊടുക്കാം.
I keep going down, but it's definitive. That's incredible. It's your show. It's your show. I'll answer. You go ahead.
Yeah.
Yes.
So we're getting back to another talk session. So I would like to welcome our esteemed guest and our speaker, Dr. Joseph Rimela, who is a senior research scientist as well as an advisor to UNESCO on international scientific programs. So he will be addressing that paper titled Responsible Innovation and Global Equity. With great respect, I now invite Dr. Joseph Rimela to address the guest. Welcome.
Okay, thank you very much. Nice to be here. Nice to, now you don't have to worry about the title. But we need the slides. No, anyways, I'll talk a little bit about what we've been doing at UNESCO Center in Trieste, Italy. And so it's called the International Center for Theoretical Physics, which is something I don't do. I'm an experimentalist. Actually, an experimental person. Anyway, but it was started by Abdus Salam. And Abdus Salam got the Nobel Prize, and everybody says, well, it's easy to have a Nobel Prize and start your own institute, but he didn't have it. He didn't get it until 15 years after the institute was open. So it just shows you somebody with passion and determination can do a lot of things. You don't need to start with a Nobel Prize. All right. And anyway, he's talking about the reason he created that center was to end the isolation of people around the world who weren't getting involved at the forefront of science, that were really kind of didn't have people to talk to. And so, and the idea of the center is to foster research around the world, especially developing countries. All right. So that's the idea. And all right, so we have quite a few. This is a snapshot of the center itself. So we have around 6,000 scientific visitors every year. They're coming from India. I think India is where the Indians. Just ran out of batteries. All right. But they're coming from around the world, 6,000 a year, but about 160,000 scientific visits since 1970. And they're coming mainly for conferences, or schools, or short research visits. We do a lot of that. Like, because it's just also recharging batteries, etc. Very important, but also to mingle with people from around the world at the highest level. So, and that's our center. I'll go quickly through this. We're part of UNESCO. Just in case you didn't know, UNESCO is the United Nations Educational, Scientific, and Cultural Organization. So education, science, and culture. I was founded at the end of World War II. I was founded in order to achieve lasting peace, not in political processes like that happens at the UN, et cetera, but through trying to bring together people on the basis of shared common parts of their humanity, science, education, and culture, and also through mutual respect between peoples. So it was a desperate attempt to achieve a lasting peace after 2 world wars in 30 years. And you see there are a couple of scientists that really were involved, really played the biggest role in starting it. They're both biologists. All right. So now on the topic of education, this is a great quote from Derek Bach, former president of Harvard University. He says, if you think education is expensive, and it is, education is very expensive, he says, try ignorance. And I think we're learning that lesson all around the world. What's the cost of ignorance? It's a lot more. Okay. So now I'm going to take a little side tour, but I'm going a little bit, I won't go out too much, because truth be told, I'm working mostly in classical physics, not quantum. I started out in spectroscopy, so I had my foot in quantum science, but I quickly pivoted to fluid flows. And so this is more of the domain of mechanical and civil engineering. And so I want to tell you that most of the universe, our Earth right here, these are fluids. most of the universe is actually hydrogen gas. If you look at it, you'd say it's 99% hydrogen gas and a little bit of other things. And the hydrogen gas is flowing. And the flow itself is not a property a matter property. It's just it's a dynamical property. So it has nothing to do with quantum science at all. So Richard Feynman, who is a physics Nobel laureate, said perhaps the fundamental equation, if we think of one for the universe, that describes the swirling nebulae, condensing, revolving, and exploding stars, is just a simple equation for hydrodynamic behavior of nearly pure hydrogen gas. And so that is in case anybody who are working in engineering with fluid flows, that would be Navier-Stokes equations. The main point here is that all of the flows are really classical. If you thought about it, why is the universe so patchy? Why are there stars here and there, and galaxies and nebulae and things? They're all spread apart. And the answer is probably there's where the quantum science comes in, because due to the uncertainty principle, there are quantum fluctuations in energy density at the moment of the Big Bang, and it expanded so rapidly, and our universe is expanding as far as we know. And so that actually magnified those fluctuations. And that's how come we have a patchy, well, that's a proposal, but that's why we have a patchy universe and not just some homogeneous distribution of matter. All right. And most of that is turbulence. And that's really been studied for a long time. Leonardo da Vinci started studying turbulence 500 years ago, and yet it's not solved. So here's Richard Feynman again. He says, finally, there's a physical problem that's really common to many fields, that's been around for a really long time and has not been solved. And that's an analysis of circulating fluids or turbulence. So anyway, I wanted to give you an idea that there are still problems. We're thinking about problems in the second revolution of quantum, but there are problems in classical physics that still are not solved. So let's see, what did Richard Feynman say about quantum? He said, I think I can safely say that nobody really understands quantum mechanics. All right, so okay, so there's a lot of big questions left. That's okay, big questions are good. It just means that you have something to work on. And sometimes you don't need to understand. For instance, turbulence, the flow over airfoils. You talk about aircraft and cars, Formula One cars, etc. You don't need to actually understand the details. You need to control it. And engineers can control turbulence. That's why you see those little winglets, the things on airplane wings. So anyway, just to let you know, there are problems, and there probably always will be, things we don't understand. So now let's get to quantum. So quantum really describes nature at the very small scales. Okay. So the word itself, I mean, we think it's quantum leaps, but it's not a big thing, it's a small thing. And it really comes from the fact that energy of matter and light is quantized in those small, discrete bundles. And those are the quanta. And this has really remarkable effects throughout the science and technology. So this comes from the work of Max Planck, who first proposes quantization of energy. And in 1900, okay, that's 125 years ago. 1905, 120 years ago, Einstein proposed light quanta, or what we call photons today, to explain the photoelectric effect. That's the effect where you walk into the store, and it goes ding, so you can't surprise the store owner. And that's what he got the Nobel Prize for, not special general relativity. All right, so quantum is everywhere. Here's a quote from Bill Phillips. Bill Phillips is also a Nobel laureate working in quantum science and technology. He works at NIST, National Institute of Standards and Technology in the United States. And he says, and I'll just read this because I think it's important. He has a way of saying it. It says, quantum mechanics change the way we think about the natural world and even our nature of reality. Uncertainties and probabilities replace the certainty and determinism of Isaac Newton's mechanics. Nevertheless, quantum mechanics is the most successful theory ever produced in terms of its ability to accurately calculate the way that matter and energy behave. Quantum mechanics has given us what we consider to be modern technological life. And semiconductor electronics is the fruit of quantum mechanics. computers, the internet, smartphones, worldwide communication, global navigation, and more are all fruits of quantum mechanics. So this is a great revolution that's been happening. It says, and a new marriage. And I was going to talk about the second revolution that everybody here is interested in. The new marriage of information science and quantum science has brought us to the threshold of a new science and technology in terms of quantum information. And that's where we get into quantum computing. All right. So anyway, he lists a lot of things: drug design, renewable energy. These are places where quantum computing will help. Secure communications are some of the areas. All right. So actually, so one of the main and most important of the quantum devices that was produced was the laser. And everybody here uses the laser. I think everybody has a laser pointer. You have a CD player, etc. So the laser's everywhere. The lasers was used to manufacture most of the things that you use every day. It was first reported in the operation on 16 May 1960, but that was 4 decades, even over 4 decades after Einstein's theoretical work on stimulated emission, which is behind the laser operation. So that's a long time from theory to actual practical device. And Myman's first thought, and this is a quote, he said, "I think the laser is a solution looking for a problem." He couldn't imagine what to do with the laser. We can't imagine what not to do with the laser. So anyway, it's the story's a reminder that the technologies we enjoy today have really arisen both from basic research and applied technology. All right. So it's a revolution. Quantum science technology is a revolution 100 years in the making. And now you're going to say, oh, wait a minute. You said Planck started all this out in 1900. That's 125 years ago. But we're emphasizing the word, and I would emphasize, really? Oh, yeah, this is a smart screen. I'm emphasizing the word technology because the technology came from the fact that Heisenberg and Schrodinger in 1925 developed quantum mechanics. That's a mathematical framework for understanding quantum systems. And without that, quantum science was not calculable. It was just a number of observations. You could make you have some idea what's going on in the world, there are a lot of insights gained, but you couldn't start making quantum things, and which we can do now. All right. So anyway, this is really going to drive future developments. And I think it's very important. We talked about, you've heard about equitable investment around the world. And I think that's very important. And there's a number of reasons why it's important. I'll get to that too. And it also inspires young people because your example, you're here for quantum. I think it's an exciting area and it gets young people involved in science. All right. Now, so in 2021, we started this journey towards an International Year of Quantum Science and Technology, which we're celebrating from 2025, and we're still celebrating it. So this is really a global outreach because we needed to campaign, we needed to inform the public, we needed to inform children, and we needed to inform policymakers, we needed to inform everybody about quantum science technology to raise the global literacy about quantum. And so this is the idea to communicate around the globe, promote its technical advancement whenever we had the opportunity, to ensure its continued contribution as an engine of sustainable development, and encourage young people again to study science. And so we had to really get a lot of endorsements because nobody at the United Nations will listen to you. No member state will listen to you unless you come show that you have a community behind you, and it's not just Greg's crazy idea or Gordon's. You need more than that. So you need to really have this coalition. So here's the path. It started in 2015 and really gained a lot of community support through physical societies, including India's physical societies. And it wasn't until 2025 that we got the proclamation. Along the way, there was a lot of discussions with delegations of member states. And that was actually the interesting part because as scientists, we can't do it. The member state has to do it, but they don't know about quantum science technology. We do, but they know that the people that are in their citizens need this, just like your government knows that India needs quantum science technology. And so how to go about this, you have to form a partnership, collaboration with them. You supply that information, they know how to get this through the United Nations. And in fact, the more you do, and it was a valuable lesson, the more you do to help your foreign policy experts get things done, the better your chances of success. So basically, you do it as much as you possibly can to be helpful, and they take it over from there. All right, so that was June 7th, 2024. It was proclaimed, and so that was really only 6 months preparation time. And it was only 6 months because we had 2 wars going on globally, and that was really consuming a lot of attention at the United Nations. And it was hard to really gather together and get a resolution on the agenda for the General Assembly. All right, so we have lots of funding partners around the world. One thing I wanted to talk about was quantum science and technology as a driver of sustainable development. So there are 17 sustainable development goals. These are just goals for countries around the world to develop and do so in an environmentally responsible way, mainly, and to actually target a lot of things like poverty, hunger, health, and education, etc. If you want to have a reference for light reading, just read this Nature Physics point. There's a nice Nature Physics editorial, just a commentary, but it kind of condenses the equations. Okay. All right. So anyway, these are the goals. And there's a lot of things listed in terms of hunger and health and education. A lot of spectroscopy for agricultural monitoring. And the use of drones is actually quite nice now. And then that's another use for drones. But that really is, we used to take a lot of satellite images and plane images. The drones make it really easy. Medical imaging. These are quantum processes. Photodynamic therapy, that's using laser to treat skin cancer. New vaccines, as we all know from 2021 or 2020. Point of care and lab on a chip. And so the last ones I mentioned are valuable in remote areas where you don't have a doctor, you don't have a clinic, and somebody is dying. Somebody is very ill, and if you can take a sample of blood and have it analyzed on your chip, connect it to a cell phone, and transmit it to a doctor in a faraway city, they can make a diagnosis, at least a partial diagnosis, and that helps. It's better than nothing. And the reason I'm mentioning a lot of things from developing country, from remote areas in developing countries, is that this is really we know that there's lots of applications elsewhere, but this is very important for the United Nations. Most of the countries, the vast majority of countries are so-called low and middle income countries. Vast majority. All right, well, this is a very special area. All right, and illumination, LEDs, etc. By the way, LEDs have been used in very developed countries, particularly in the north, in Scandinavia, because you can tune it. It's a digital light source as opposed to the filament light bulb. So you can actually tune the spectra, and so you can make it match the diurnal variations of light. And that's actually much healthier if you can fool. I know you're not supposed to fool Mother Nature, but sometimes it helps. All right. So there's lots of things. Education again. So this is Bill Koglaser. He worked on the State Department, but he's talking about education. He said building human capacity is the key element in producing and creating an innovative society. That's exactly what we're talking about. This is a holistic approach. It's not just strengthening research here or there. It's a whole holistic approach that includes education. At the younger ages, it includes public engagement, outreach, everything. He says we have turned off too many young people from science by teaching in boring ways. Nobody here, that doesn't apply here. But emphasizing memorization of facts rather than teaching by inquiry. And some of that is because schools are really geared towards standardized tests in which the large numbers of students don't pass those tests, they lose their funding. So they teach science by memorization, teach all subjects by memorization. There's a negative. So anyway, and then we also have teachers who are not adequately trained. sciences and mathematics. That's everywhere, including the industrialized countries. Really, especially at lower grades. All right. So and Giorgio Parisi is a Nobel laureate, a recent Nobel laureate, also in quantum areas. And so he's really thinking we need to get hands-on. Need to get hands-on. This is that inquiry-based education that Bill Kohlblazer was talking about, and we need to do it at an early age, even at kindergarten. Kindergarten is not too early to start kids doing experiments, to learn with their hands and to use their minds, not just to absorb. As Yates once said, education is not the filling of a pail like pouring knowledge in, it's the lighting of a fire. That's the way to look at it. All right, so, and the other thing he said was, in scientists, and in you, students, you can do this too, just talking to the general public, your parents, but also your kids that are younger than you, because this is how you get a public that is actually informed about science and gain some of the trust that we've seemed to have lost. And it's not trust in science itself, it's trust in that scientific method. It's a self-correcting method by which bad science eventually gets thrown out and good science replaces it. It's the best thing we have, and it actually works. All right, and so that keep going. And so we've been doing things in UNESCO for teacher training. You might not be interested in this so much, but we're trying this a multiplier effect. So you teach one teacher teaches a lot of kids. That's the idea. But this is in optics and photonics. So these are quantum areas. And we went all around the world, where there's a number in parentheses. We went there that number of times. And you see there's actually here, this was in Miranda House in Delhi. It's a private women's college in Delhi. And that's this handsome gentleman here with the red dot on his forehead. What do you call the red dot? Oh yeah, okay, I knew that. Well, anyway, so he's a CEO of SBIE and they're a funder. So he came along to see what was going on, which is good because you want your funders to come and see what you're doing, and because accountability is great. And so he was one of the students. This is actually a picture from Kiev back in 2017 when things were relatively calm. And also, these are two students on my left and two students on the right. All right. Also, outreach, and this is what I was just talking to you about, because these are undergraduate students, but this is in your neighbor, Pakistan. So these are undergraduate women at Qaid-e-Azam University. We chose to keep it segregated like that. And the idea wasn't just to teach concepts, it was to have an enjoyable day of hands-on learning. Just enjoyable. I think that word that needs to be emphasized. If you could have an enjoyable day doing science, you're more likely to keep going, because otherwise it's pretty hard. You need a little break. All right, so but you couldn't get them away from the lasers. All right, so finally there was a quantum education event held in Accra in August. And it's also Accra, Ghana is the host of the closing ceremony coming up in February. And we had many people. This guy right here, Richie Mike Wellington, was somebody I've been on the phone with since 2021. And we've been going back and forth daily because he was the leader on the member state side to get this whole year under control. And he's with the science minister there. All right, so one of the things is the International Day of Life. That's another observance, kind of a global outreach event. It happens every year on May 16th. And why do we pick that day? Anybody have an idea?
Introduction, please.
Yes, all right. You get €5 from Greg. Okay, so at any rate, it's the same thing. It's to raise awareness of the importance of light and light-based technologies. They're really quantum devices. And we've reached people from all around the world, including we had two Russian cosmonauts on the space station that gave us a special message. All right. So finally, this is I'm getting to my last slide. I want to talk about education innovators in the old days, before the age of innovation. Right now, we're talking about inquiry-based learning. It's a buzzword. It has a lot of implications for using prediction and testing and discussion, et cetera. But in the old days, it was mainly to get in the classroom and to get lectures. And this instructor took her kids up to the tide pools, and this is in the state of Oregon, to learn about marine biology, but not marine biology in the textbook. Just go out there and immerse yourself in a tide pool and learn about that, but also learn respect for living creatures, respect for each other, because these were kids who really came from very broken families. They're special kids. And I think our schools, nobody wants a disruptor in the classroom. I mean, that's easy to understand. But sometimes, and you have kids who are underperforming, they're teenagers, and there are some emotional issues, and you don't want to throw them away. But schools being pressured for standardized tests will throw them away. They will find a way to get them to go away so they don't lower the average score. So this is not okay. And anyway, so this was back in the gentler time when that didn't happen. And the last thing I want to say is these are my heroes, both these guys. So Doc Ricketts is a marine biologist. I actually read his textbook. And John Steinbeck was a Nobel Prize winning author. And he wrote about the Great Depression in the United States, the effects of the Dust Bowl. But he wrote something called Cannery Row, which he featured a guy called Doc Ricketts, who was really a doc. He really wasn't a marine biologist. And they ended up writing a book together. So a scientist and an author getting together and doing something. So this is a cultural aspect. Because I think it's really nice to get that connection. Well, anyway, it's just nice to see. All right, so now I'm going to end it. So just concluding, we could have had a celebration of quantum science technology amongst physicists and chemists and biologists, whoever was interested in the science sector. And we could have patted ourselves on the back. That's what obviously we can do that. Say, wait, great job we've done over the last 100 years. Look at all we have. All we've accomplished. But we didn't think that was enough. We thought this was the higher calling. It was actually to bring this message around the world, get people to understand what it is, actually to bring that out. I told you it was important. I think it really is important for you, for me, for everybody to go out and inform and try to educate, because we're all teachers. Try to educate your parents, your fellow citizens, and younger kids coming up. And I think that's what we're really going to need, because as I said many times, I say it to scientists and they all cringe. I say scientists are not going to come up with solutions to societal problems. And they go, what? Are you crazy? No, but scientists will come up with technological solutions, no doubt about that. I'm not saying they won't do that. They will come up with great things like the laser. They will come up with fantastic stuff, but that doesn't solve a societal problem. That's just the technological edge that allows you to do that. You need everybody, because you have to get it introduced. You need politicians, you need lawyers, you need ethicists, you need everybody involved, philosophers. You need other people involved. It takes a whole community to solve a community problem. Well, that's why that's the important part. If you really want to improve the quality of life. And I think that for me is the ultimate goal of what, if I'm an engineer, I want to improve the quality of life for everybody. I mean, what's the other goal? Making money. Maybe that improves my quality of life. But even for a theoretical physicist thinking about the cosmos, if they understand it, that's improving their quality of life. Okay, and I think if you're improving the quality of life for everyone, everywhere on the planet, that's a pretty nice goal, and that's what we're kind of after. Very simple goal. All right, well, that's it. Stop right there.
Tom is the president and CEO of Colloquium.
Yes, thank you.
Microelectronics Corporation, by the national initiatives to advance Canada's microelectronics, photonics, and quantum technology ecosystem. Seasoned entrepreneur and technologist, Carly has founded and led several companies in semiconductors and secure technologies, including gold semiconductors and electric technologies. I invite you, sir, for the keynote address.
You did a lot more research on me. Now I hope I don't look as silly as Joe. Yes, hello. So it keeps on saying doctor on all of your stuff, but I don't have a PhD. I have a master's in engineering physics, so I'm going to talk to you about how to make things. So CMC is a not-for-profit. We've been around for 40 years, and recently we got funding 780 crore rupees over 5 years to stimulate fabrication of advanced technologies in Canada, microelectronics, photonics, sort of thing. And so I'll talk a bit about that program, but also we have commercial revenues. We actually help out companies small and large. And we have customers in 22 countries, so we offer our services everywhere. But as I talk about the services we offer, I do want you to think, how would you do this in India? How would you replicate it? How would you make an Indian version of these kinds of services? And we would be happy to help you with that. Try it in. That's too much? Yeah. So, as I say, we're not for profit. We serve actually much closer to 12,000 people. We do provide them the tools and technologies. And these are the key areas we serve. Microelectronics down to 12 nanometers. We purchase that from factories, photonics, IoT, which includes some AI, and maps, which includes packaging. So we do custom packaging for people who have a specific need. And as of about 6 years ago, the very first IBM Quantum Hub came to Canada, and we bought a 1/4 share in it. And so we have access to all of their largest machines. And we provide software, but we also love hardware. So I'll talk about building your own quantum computers. They're in India. We do not worry about what your application is. We give you the tools and the technologies, what we call horizontal infrastructure, so you can use that to build whatever you want to. So social engineering, social learning. I have a very much a Canadian sort of perspective here, but as I say, we work in many other countries. There we are, national users. So we do have orders from India, sometimes for fabrication, and so we've been talking to some of the IITs as well, about Canada. And we operate a supply chain across the world. Over 100 companies supply us with wafers and packaging and testing and so on. There are similar organizations to ours. Europractice is actually a blend of 5 different organizations, and there's IDEC in Japan, IDEC in South Korea. They all have different models. Most of them fund 100%, and researchers can just get the services for free. We are a bit unique in that we heavily subsidize a lot of the stuff, but people do have to pay a fee to use it, and we help use that to help dynamize the system. But we have regular phone calls with all of these folks, and we compare notes and talk about new best practices and new services and all that sort of stuff. Then complain about our funding. So we got this 780 crore rupee funding over 5 years, and so last September we opened a competition. And for 2 weeks we asked people, do you have a project for us? And we had 138 expressions of interest. We turned that into 67 proposals, and we funded 20 of those. And that creates a total envelope of $35 million. We only put in about 13, so it gave them sort of 40% subsidy. But that's led to a lot of electronics development in Canada. Half of it was developing new process technologies in existing factories, and the other half was taking the sensors that they developed and putting them into IoT devices. And those went into healthcare, they went into agriculture, they went into a whole variety of applications. We picked, in Canada, we have factories for compound semiconductors, MEMS, or micro electromechanical systems. These are mechanical sensors built using semiconductor style technology, and then photonics and superconductors. And you have SCL Morelli, which actually builds MEMS, and it actually builds semiconductors here in India. And they actually did a 46 student designs just recently. So it's my bit of research. Yeah. So the three services we offer, we call CAD, Fab, and Lab. We offer design and engineering support. So we have about 30 technical staff, mainly PhDs who can help you with a piece of the design or with consulting or whatever you happen to need. And we have tools from a variety of vendors. So we sort of have an attitude that we would like you to use commercial tools that are industry ready. So when you go to work at Intel or work at AMD or whatever, you show up with the knowledge of the tools. There's a big swing towards open source today. And so a lot of people went in high school and stuff want to do a chip. And you can do it very cheaply through folks like Tiny Teeth out in Wakerspace. And they have for a few $100s, you can do a chip and run it through. But it's good training. You do get to know the tools, but we would like people to come out of colleges and universities with industrial training. So we negotiate excellent deals with these tools. Cadence, Synopsys, and Siemens, who all do microelectronics design stuff, would love to give India free tools. It's a matter of how you set them up in the cloud and host them and all that sort of stuff. So it's the hard part, I guess. And there's lots of intellectual property available, again, typically free to universities, like ARM microprocessors, the RISC-V microprocessor. We have one that you can download off our website for free to get a microprocessor up and running. You can put those into FPGAs, you know what those are, or you can develop the different chips. And the way that we do fabrication is many of the factories do not want to talk to an academic or to a small company. And so we will take 20 designs and bundle them together, and we show up and we pay, it's typically $200,000 to $500,000 is the minimum purchase. And so we pay that and we fabricate it, and then we split the bill among all the people who are on that run. So you only pay for the area that you use. So it's a very cost-effective cost-effective way of getting 40 or 50 samples. So you can drop a few, burn up a few, put a supply pile on them, and then finally get a device to work, and then use that to either attract an investor or convince a client to use you or go publish your research and so on. So we do over 400 designs a year, unique designs in about 60 different fabrication runs. And it turns out to just be a much more elegant way of getting your chips done. So in Canada, many of the universities have little micro fabs where they can do MEMS devices or photonic devices. There are 44 of them. And we have a lot of discussions around that, and we find various equipment at different places, atomic wave deposition or plasma etching, whatever. But we recently joined a global nano lab, and this is Australia, Japan, the US, Canada, and Europe. And so I will try and find the appropriate person at SCL Morale and see if we can get India to join as well. But the idea is that it's free. It's just it's a group of people who are sharing ideas about how you do deposition and etching, which machines you've purchased that don't work, and what kind of problems you're having. So we can share ideas. So that would be a great place for you to get more and more information about what's happening elsewhere in the world. We really like the idea of students learning how to build a device and then test it. And so we offer this base camp training. This is offered everywhere, but basically we have a variety of courses already developed. And you have 1 or 2 weeks of intensive training. You can be online. And then we leave you with tools in the cloud for 2 or 3 months. You complete your own design, you submit it, we fabricate it, and you're expected to test it. So some universities are putting the course in the first VLSI 1 or Photonics 1 course, and in Photonics 2, you have to actually do a test and test your chip. So it's great if you can build a chip and then it doesn't work, but you can try to figure out why, and that's fantastic training. You've done your first mistakes on our dime and not on your company's. So it's very attractive when companies hire you. And we have LDCC for packaging as well, and the rest of relatively inexpensive ones. And we also offer these same services to startups. And so small companies that want to do a first design, want to do a product, they can join our virtual incubator environment. And so there's a complete offering there. But of course, I'm supposed to talk about quantum computing. So 6 years ago, we started our own quantum computing group. We had access to the IBM machines, but over time, we've added more and more machines to that list. We offer this is quite new, called the Quantum Sandbox, where people can come in and do a very short project with a lengthening as they go, and our people will help you. You can either do the coding yourself, and we just help you tutor, or we can help you. We can do some of the coding as well. And we have a variety of machines: IBM, Pascal, through an entity called Paint, Continuum, or Giddy, Cura. There are others, Anion, Xanadu aren't mentioned there, but there are 7 different quantum machines on Canadian soil right now. They're all accessible by the web, so you can code on them. And if you want to get in easily, then you can actually use high performance computing, the data center computation to simulate quantum. So you can try that out and try it out on small problems, and when you get to bigger problems, you can bring one to a real machine. Our own group has done 30 quantum computing projects. It's really 32, but 2 are for defense, so I can't talk about them. And of these 30, 27 were academic projects, and 3 were industrial. I asked them what the results of the finance one were, but they wouldn't tell me, so now. And then we have a number of publications that came out of this. These are all with Canadian entities for the most part. So feel free, if you look at our cmc.ca/quantum, you'll see the list of publications and all through. This again is the R&D projects roadmap. So lots of support there. But we love hardware. And so about 5 years ago, we started the world's first superconducting design course. And so we offer this application every year. And you can build transmon qubits or single flux quantum circuits, SFQ, or squids for MRI machines. So you can design and build these yourself, and we ship you the chips. The trouble is, you do need a cryo fridge to measure them. That's part of the deal. That's it.
Is there any possibility for us to associate with our institute?
Yes, absolutely. Yes, for sure. In fact, NIT asked me if we could sign this early, and very lively and open, but they're talking about what projects we specifically do in the future.
Yeah, because we have electronics department students are there,
Yes.
so we can do a lot of flow service.
So we have a number of IoT devices
Yeah.
designed that you can download for free.
Okay.
Actually, one of the ones was for healthcare, but it was actually for testing rats. So it had probes that went into the rat's brain to measure anesthetic levels, and then it used an inertial measurement unit to determine exactly how the rat was moving. So different anesthetic levels, you Bluetooth out the data. So we carry a backpack, no tether. But you could imagine this, the different sensors that could be used in many different applications.
We will discuss and I think we can connect with them.
Sure. Thank you. So, thank you all. Yes.
Copy ചെയ്തു പേസ്റ്റ് ചെയ്തു സൗണ്ട്
യൂട്യൂബിൽ തന്നെ
അത്
ഇതല്ലേ പേഴ്സണൽ ഇതിനകത്ത് പിപിടി ഇവിടെ കണ്ട് ഇല്ല ഇപ്പൊ ഈ പിപിടി രണ്ടെണ്ണം അവിടെ കിടക്കുന്നു ഒന്നങ്ങ് ക്ലോസ് ചെയ്യും
ഈ ഫോൾഡറും വേണ്ട ഇതെല്ലാം ഇവിടെ കിടപ്പുണ്ട് ഇവിടെ ഷെയർ കൊടുത്ത്
എന്റെ സ്ക്രീൻ
ഷെയർ ചെയ്തിടും ഇനി നമ്മള്
അതിന് സ്ക്രീൻ അങ്ങ് മാറ്റിയാൽ മതി താഴെ കിടക്കുന്നത് ഇട്ടാൽ മതി
മതി.
Yeah.
I'm so excited.
Thank you. More guests. Yes. Lots. Maybe like this. Oh, that's wonderful. I don't know that I need it. I'm from New York City. Yeah. You can you hear my voice in the back, right?
Yes.
That's too bad. Okay. Well, thanks for coming and listening into all of the folks today. There's so much information about quantum. My section of quantum is on security. And first of all, I took some notes, just take a second here to remind everybody that if I see anyone using their corrugator supercili, their Proceras, or the depressor Angligorius, I'll be very unhappy. Those are the major muscle groups that make me frown. I don't want to see any frowning. The security is scary. I could list all the muscles that I want to see you use when you smile, because you all love security. Maybe we won't do that. So I am a hybrid. I came from the medical field. I started as an infantry paratrooper. I was taken into the medical field by the Army. Why? I don't know. But they chose me to go and I do medical research. I did medical research for a couple of years on a great virus called Eastern equine encephalitis. Mapping genomic processes. It was delightful. It was science. I get to do science stuff. And then they came over to me and said, you're going to leave science and you're going to go over to the National Security Agency. Anybody hear that? Yeah, I heard it too. After I got there, I heard of it. I didn't know about it until I got there. And I wasn't doing science anymore. I was doing intelligence. I was doing assessments. Wasn't excited anymore. But I also got to work. The FBI. I worked with Interpol. I worked with the UN Office of Drug and Crime, doing a lot of investigations. And this is where I learned about cyber. And I started to work with cyber all the time. Everything I did was cyber. Mostly on the offensive side of cyber. So if you needed someone to break into a cell phone or a computer, I was that guy. And I was pretty good at it. So let's see. You have a cell phone with you? Can I have it? I'll just get it fun. It's okay. There's. Just 2 seconds. Okay, good. It's okay. It's okay. Okay, great. Now, maybe you. Do you have a cell phone? You do, because it's sitting right there. You don't have to unlock it. It's okay. It's exciting. Oh, you do? No, that's good. Cool. It's exciting. Thank you. Okay, I'm done. Now you all have all of her data. Wasn't that nice of me? Just share all your data with her. Is that okay? Yeah. I'm not allowed to do that here, but I did it at a demonstration at a hacking conference in Las Vegas called DEF CON. Doesn't take a lot for security systems to break down when you rely on technology. Security starts a long time before technology. It starts with us. It starts with people. India is a trust society. It's a trust system. Where I come from, in Virginia, it's a trust system. In New York City, it's Maybe it's not a trust system in New York City, it's crazy. But many places around the world, Canada is a trust society. We trust the people we work with. That's good. Because we should trust our friends, our neighbors, our families. We shouldn't trust people that are mean, bad, ugly. People that want to do your society, your family, harm, steal money, abuse you, abuse older people, not respecting older people, bad things. What we want is a society that can create a security system that they are safe with and can use safely and smartly. We're still on slide 1. Quantum security starts with the trust systems that we have as students, as teachers, as brothers and sisters, society. That's where all security starts from. And I don't like to say cybersecurity. Where's all the computer science? Nobody's in computer one. Really?
Yeah.
I've been talking for 10 minutes. And she's already asleep. It's okay. So computer science is about building, managing, controlling all of the networks that we have in a safe way that people can use, that they feel safe using them. Cybersecurity, you may believe this, does not exist. Computers have been around for 40, 45 years. You know of anyone who's ever said my computer is secure? I can tell you, I've broken into some computers that were supposed to be secure. For many years, they believed they were secure. It wasn't the case. Nobody's computer is secure because there's too many variables that affect the technical security in a computer box. That's the problem. So computer security is not there. What you have is a system of risk management. You're managing what you can accept as the risk to operate your computers. Your administrative computers are just as important as your operational computers. Well, think about that, because the administrative computers run and manage all of the people. It manages everything that people are about. Operational computers manage everything you use in the factory to make products. They're just as important, but neither has a security system. Both have risk management systems. So, since you were very helpful before, you got me coffee, and I appreciate that. What, you're going to be a computer scientist? That's very definitive.
No, because I'm not choosing one being specific.
Are you going to be a teacher?
No, definitely not. It's not.
Okay.
Like with cloud computing. Trying things.
Okay, good. You're trying. That's good. What about you? What's your major? Smart. Okay. Are you going to be a teacher? Maybe. Can't hide by looking away from me. So I'm going to come right over here. Electronics. Are you going to be a teacher? No. I didn't come here right in front of you. What's your major? Electronics and communications. Are you going to be a teacher? Definitely no. So I talked Very smart people. Nobody wants to teach. Think about that. Who in here wants to teach? Show of hands. I know, because I saw you before. You're like, oh my gosh. If you're not gonna teach, who's gonna teach the kids? After. Who's gonna carry on the legacy of learning? You know where you're gonna be in 10 years, 20 years? I didn't know. Like I said, I started as an infantry paratrooper, jumped out of planes. Crazy. Then I'm in a medical lab. And then I'm doing cybersecurity. Then I'm doing investigations for the UN. Holy cow. My undergraduate degree was liberal arts. Has nothing to do with anything that I've done in my life. Nothing. You're going to end up teaching. Why? You're already doing it. If you have brothers and sisters, you're teaching them. Your parents, you're teaching them. How am I teaching my parents? I'm teaching them about the younger generation. So they can relate to you and to other children and to other young adults. Teaching is one of the most important things you can do because education and information is central to my topic, security, but it's central in a societal manner, taking care of everybody you love and everybody you know. Joe said earlier, you know, education's expensive, but how much more expensive is ignorance? That's a very, very, very important thing to think about. We have to be educated. We have to learn. We have to pass that on to the next generation. Every parent always wanted their children's life to be better than theirs. They wanted just a little bit better. They want more for their children. You're going to want more for your children too. If you do that, you have to learn and you have to teach. There was a guy who wrote a book a number of years ago, The 7 Habits of Highly Effective People, Stephen Covey. I'm sure you all read it here. I have. Habit number 5 is my most fascinating habit because in that book, Stephen Covey says, seek first to understand and then be understood. You have to understand. You can get information, but what does it take to turn information into knowledge? What does it take to take information into knowledge, into wisdom? And in that, you will prepare the next generation. We just had a very important VIP here this morning. I don't know if you saw her. She's pretty smart. The medical doctor. Got a PhD from Syracuse. She got a, master's in public administration from Syracuse University. She's been in several of her cabinet positions. One of you could be her in 20 years. You could be sitting in her seat. You could be the governor of the state. You don't know. You're going to be the next policymakers. You are the ladies right here that are the leaders. Can't lose that opportunity to learn, understand, turn it into knowledge, and then wisdom. Wisdom to help yourselves, to help others, and to understand all the way through. So let's talk more about security. Because if you don't have wisdom, risk management in cyber is a big problem. I'm not saying I'm smart. I'm just saying I've been around a long time and I've noticed a lot of things. Now we can go to the second slide. Or not. On the pointer, Joe. There it is. There it is. Did not work on the screen. Hey, all right, there it is. Thank you. That's cool. Quantum cybersecurity is not about quantum computers. It's about security. It's about risk management about quantum computers. Okay. We have tons of data that's out there. You've heard about the harvest now, decrypt later concept, right? It's very real. There are a lot of large data sets to talk all about you that are already out there that are compromised. Who goes into the dark web every day?
Sometimes, out of curiosity. Yeah.
Yeah, I'm in the dark web all the time. Good places. And if you see me there, don't let me know. I don't want to know. Okay, but it's part of my job because I do investigations and I collect information. And I still work with an FBI task force, rolling up people that are doing bad things in the dark web. Okay. All of your data is in the dark web. I want you to understand that. Like I said before, there's no computer that's been secured. Every computer is either hacked or has been hacked and you don't know it. And why do I say that? Because even the best, most secure systems, it takes on average in industry 206 days to identify that they've been hacked. In 206 days, I believe a criminal can take every bit of data from any organization. It's a guess. I think 206 days is plenty regardless of how big the company is. Ford Motor Company, 2008, was hacked. They lost everything. They found out 436 days later that their data was compromised. That means everyone who bought a Ford, every entertainment system in the Ford vehicles themselves, the hackers were able to track every person who owned a Ford truck. Why? Because of something we call TPMS, tire pressure management system. They were connecting their devices to the tire pressure management, which connected to the internal computer in the car, which sent a GPS locator to identify what the car was, number one. Number two, it sent an LTE signal out to connect, to remind people in there that their tires were low or that they needed maintenance. But when it did that, it took all the information off of the central computer in the car, sent it along with it. That means that everything was taken. This happens over and over again. So if I want to know that somebody's not going to be home, I already know because basically if they have a Ford, I can track their car and I know where they're going. And I know that they went to school or they went to work and they're not at the house. And their Android phone, Samsung has been hacked. I think they have had about 15 data breaches. Anyone with a Samsung phone here? Maybe one or two people, okay. Yeah, all your data that's stored on your phone, your passwords, your email, all of that is compromised. It just hasn't been sold in a dark web market yet. That's all. So remember, there's no such thing as security because there's too many variables. What you have is risk management. What do I have to do to make my phones more secure? So somebody won't be able to easily get access to what I have on the phone. That's what we think about with quantum. So when we look at long-lived data, we have data sets because we've put systems in place that require long-term protection, but we don't protect it for a long time. Here's a quick, because I'm an epidemiologist and I'm a public health doctor, I give you public health data. I know engineers, science people, it's okay. This isn't going to hurt, trust me. What we have here is a disease. This is when it came up. This is the impact in the region in India. And over here, what it means, long term. Every one of those diseases that hit India, data was collected all throughout the country into systems that weren't designed to hold the data for more than 3 years. The security that was put in place to protect all this data was useless decades ago in many cases. Let's take a step back. Let's look at the world. How much data has been compromised in these disease surveillance systems around the world? That's a lot of data. Took me a while to make that slide because I wanted to get some good diseases. These are the ones where most data is collected. The reason I include the influenza pandemic in 1918, the first one here, is because that one spread around the world. And that data was secure. Well, let's see, 1918. When do you think the data wasn't secure anymore? Anybody take a guess? 1919, right, exactly. The data was no longer secure within 1 year. And data was already being spread around. Imagine what it was like with the COVID data that you were told was secure and safe. It really is huge data sets lying in the dark web. And they're accessible to anybody and anybody who wants to pay the price. So we're not going to talk about post-quantum cryptography because that's just silly. Anybody know what Shor's algorithm is? Great. Everybody in the negative sense has acknowledged they don't know what Shor's is. Shor's is an algorithm that is used in quantum to figure out and break cryptography. Shor's algorithm is an exponential algorithm. Instead of n, you have 2. Grover's algorithm, quadratic algorithm. Algorithms of this nature are the best things that are available to break quantum cryptography, or that can be used by quantum computers to break standard AES 256 encryption, which is what we use for email, for government work. Every country around the world uses AES 256 encryption for most of their government work. Okay. Grover's algorithm, quadratic one, the best it can do right now is to break down AES 256 to AES 128. It's the best it can do. And it's going to take longer than the Earth's been around to do it with a quantum computer. How cool is that? Quantum's not necessarily going to break your cryptography. What it will allow people to do, cryptanalysts, people that look at and figure out how to break codes, it'll let them break away different parts of how ciphers are created to build code. And it will also help them identify the weakest part of any cryptographic system, which is you. Biggest link in risk management are humans. Why is that? because we have high trust societies. And I'm not saying it's bad, but we have to understand that in order to get into future technologies safely and to use them responsibly, we have to understand really what society is and who's involved. And that means we have to be able to figure out who the bad people are, but not create terrible restrictions on the people that we trust and we work with. And that's hard. With that, post-quantum cryptography is not quantum security. We talked about that. Technology upgrades does not make a company safe. Anybody use Microsoft Windows? Oh, put your hands down. Okay, let's not do that again. Let them use Linux. You're my people. This is great. Linux is an operating system that you can take and control and set security and do all kinds of things the way you want to do it. Okay, just point of order. Let's say you have a Microsoft Windows box, right? And there's a vulnerability that's listed. Somebody comes out and says there's a vulnerability. Then it doesn't matter what it is. Now your computer is vulnerable. That's what we call bad. It takes Microsoft 2 to 3 days on a simple exploit to create a patch that's going to be tested, vetted, so it can be sent out to everybody's computer and fixed. 2 to 3 days. That's great. Microsoft super responsive, except that you can get ChatGPT to write an exploit in 15 seconds. So if it takes 2 days to patch a computer and 15 seconds to create a virus or a bug that'll infect a computer, who wins? Not Microsoft, not us. That's why you don't have security. In this technical world that we live in, there really is no security because you can't fix it fast enough. You've heard harvest now, decrypt later. That's been going on for years, and it's going to continue to go on. But again, as I mentioned before, the different aspects of the system itself will be hit with quantum capability to break it down and tear it apart. Okay? What's one to break first? Trust system we're talking about is the first thing that quantum breaks. Does anybody disagree with me for what I've talked about? That's what's going to go first. You'll lose faith in the system that's there. Talk about quantum capabilities to break cryptography is true. It'll eventually become a problem. Is it a near-term problem? No. Is it in the future? Yes. It'll eventually be in the future. Quantum fixes or looks at and analyzes great problems like NP completeness. Like logistically, how do I get things from here to here for the least amount of money, the most efficiently, the most effectively? How do I use the system that I'm going to power a city with? Quantum is very good at that. But traditional math like this is not something that quantum does extremely well yet. But it breaks trust systems, the digital identity systems. It will, the systems that control and manage long-lived institutional records. digital platforms, and then, of course, cross-border data exchange. How many people come into India every year? Anybody, real quick off the top of your head now? No? Nobody knows, really? Well, I don't know. But it's a big number. It's a big number. That's a lot of people moving a lot of data. Those people are coming in with cell phones. People are coming in with computers. They're accessing the internet here. They're accessing data here. One of the most important things, I think, is understanding that here, in this classroom alone, you ladies have solutions to some of the most important problems facing India and the world today. You don't know it yet. Anybody know when was email invented? Email. That's great to shout it right out. 1971. That's right. Exactly. 1971 it was invented. Oh my goodness. When did we start? That's a long ways away. How about the first wireless communications? 1890s. Wireless communications, and it took us this long. How about cell phones? When was the concept of the cell phone first formed? Anybody? 1930s. First functioning cell phone was when?
I'm
I'm gonna take my €5 back. It was in the 70s.
That's what I meant.
That's exactly right. That's what you meant. My point is that these technologies were thought of, they were dreamed up. First concept of a computer, it was an analog computer, I get that, 1836. These ideas came from a long ways away. You might have those ideas in your head right now, or you're developing here at school. You could be the people that patent those ideas. You could come and solve the problem that we're facing, quantum risk management. About leadership, about policy right now, not about functioning or executable capabilities. We have to have governance, policy, match up with education, with capability that teaches young people to be the leaders, to continue that process forward. You have to be the people to learn different aspects of what's important, because governance is key. If you lose control of technologies, it gets out of the hands of good people. It's very bad. 1990, 1991, 1992. World was very stressed out. What had happened? The wall that divided East Berlin and West Berlin had come down. Communists in East Berlin and East Germany, the government had fallen apart because the Russian government was falling apart. Soviet Union was dissolving. One of the problems we faced, we didn't know where all the nuclear weapons went. That's a problem. You might be a little bit young to remember, probably not born, but most of the world was extremely stressed out, not knowing where all these nuclear weapons were for 2, 3, 4, 5 years. They were missing news. Governance is so important. Managing, controlling, understanding. If the technologies you develop, and you should be developing here, if you develop them here and you control them here, we won't have a problem with that. Okay? There was a young guy I saw a place ago. He said, I really want to build a cell phone. I said, do it. He said, government won't let me, too many controls. I said, okay, those, you're talking about pulling out all those facial muscles and putting on a sad face that I can't do it. I said, you have to go talk to your teachers, who can talk to somebody who's in business, who can talk to someone in government, and create the solution here in India. You own it. You're not relying on China. You're not relying on the US. You're not relying on Japan. You're not relying on South Korea. You build it here. Build the trust system inside of India. And that's what we want to help do. So thank you for your time. I appreciate it very much. Questions? Okay. Does anybody have any questions? Open. Okay. All right. No questions. There you go. There you go. Thank you very much. Thanks.
Thank you so much, sir. So as we conclude the Global Quantum and Exponential Technological Meet, I extend our sincere gratitude to all who made this international colloquium a grand success. First of all, I would like to thank our offline speakers, Dr. Wayne Hicksik, Gregory Carpenter, Dr. Joseph Mimela, and Mr. Gordon Howling, for their inspiring presence and insightful addresses, which really enriched today's discussions. Thank you all.
Thank you.
We also express our heartfelt appreciation to our online speakers, Dr. Harris Ariel, Dr. Thomas Clausen, Dr. Luigi Serio, and Dr. Dino Cataldo, for joining us virtually and sharing their valuable global perspectives. Our special thanks to Shobha Anand for her guidance and support.
Really acknowledge the effort of the organizers who participated. Finally, we thank all the delegates and the participants for being.
So, thank you guys so much for that.
Thank you everyone so much. I hope today was, how many people think it was helpful? Anyway, I do hope this one was helpful, but sometimes also you don't understand things right away. Home and think about it. And so you have our contact information. You can, contact us with questions and so.